At the dawn of the universe, there were no planets or stars, only vast clouds of gas and dust. It was within the dense centers of these clouds that conditions were ripe for the formation of our sun, the solitary star of our solar system. Subsequently, the scorching solar winds fused with the materials in that path to form Earth, the place we call home. At that time, there was no sign of water within the solar system. So, how did our Earth come to possess water? Presently, Earth contains approximately 1.386 billion cubic kilometers of water, nearly as old as the planet itself. However, indirect evidence suggests transforming a barren rock into a unique water-filled planet. Around 4.6 billion years ago, when Earth was forming, the initial environment was extremely hot. Resembling a massive molten furnace with absolutely no water in its liquid state, this era is known as the Hadean or Kirkwood. About 800 million years later, as Earth's temperature gradually decreased, the planet underwent a period of intense comets and asteroid bombardment known as the Late Heavy Bombardment. It is during this time that Earth's aqueous environment likely took shape, with both seawater and freshwater partially contributed by cometary ice. This hypothesis has been so prevalent that it has almost been accepted as fact. However, as time passed, evidence to the contrary began to emerge. In 1986, the European Space Agency's Giotto mission, the first to closely observe Comet Halley, found that the comet's water contained twice the amount of heavy hydrogen deuterium compared to Earth's water. This difference in heavy hydrogen content indicates that water on Comet Halley is distinct from that on Earth, casting doubt on the theory that Earth's water originated from cometary ice. After observing Comet Halley, scientists studied other comets from the Kuiper cloud, only to find that their water, too, was different from Earth. Consequently, scientists have mostly ruled out the possibility that Earth's water came from cometary sources. Despite this, not all comets are the same, and attention has shifted to the asteroid belt closer to our solar system, where scientists hope to find water similar to Earth's. In 2004, the European Space Agency launched the Rosetta probe with the goal of landing on an asteroid from the asteroid belt named 67 Gerasimenko. While the mission succeeded, the results were disappointing. The water on this comet had even more deuterium, 3 times more than Comet Halley. Observing multiple comets yet finding none would matter similar to Earth's led many scientists to question the cometary water origin theory. Why? And as Stephen Murchis, a geologist from the University of Colorado, is a specializing in diopside crystals. Diopside comes in a variety of colors, and it can sparkle like a diamond at a fraction of the cost, making it a popular substitute in jewelry. Moses suggested that instead of looking to comets for the origin of water, finding evidence in Earth's rocks would be much more feasible. Initially, geologists scoffed at Moses' conjecture, considering it overly fanciful. Geology posits that Earth is a dynamic body, capable of recycling its crust and processing these recycled materials under higher pressure and temperature within the mantle, and finally ejecting them back to the surface through volcanic eruptions. As a result, Earth's crust is a cycle at renewal, and finding materials from Earth's infancy over 4 billion years old on its surface is exceedingly difficult. However, Moses' idea gained traction when, in 2001, a collaborative research team from the University of California and Princeton University found epoxide crystals dating back 4.4 billion years in Western Australia's Jack Hills. This discovery caused excitement as it provided a chemical fingerprint from when Earth was just 100 million years old. The team determined that the crystal's isotopic oxygen content indicated the presence of water in its liquid form 4.36 billion years ago, suggesting that seas or freshwater lakes cover Earth's surface, at least in some regions. Since 2001, over half of the diopside crystals collected of characteristics of water in action with rocks and display signs of alteration by water, forming clay, while others show evidence of hydrous melting, which naturally involves water. These findings cast doubt on the late heavy bombardment theory of Earth's water origin, as the evidence points to a much earlier origin. The mystery of Earth's water's origins persists. How did water come to be on Earth if it didn't come from comets? Alexander May, an astronomer and mathematician, proposed a new theory for the formation of planets in the solar system, which also explains the origin of water. Lee argues that during the early stages of the solar system, there were not just the 8 major planets and where today but allowing 15 smaller particulae, where Mars is currently located. In this region, the high temperatures lead to the formation of dry planets. Beyond this boundary, where temperatures were lower, what planets capable of retaining water could exist? Over time, the gravitational interactions of these early protoplanets led to collisions and mergers, to forming larger planets. The formation of gas giants like Jupiter and Saturn dramatically disrupted this initial equilibrium. The massive gravitational pull of these giants, with Jupiter being more than 300 times the mass of Earth and Saturn 95 times, significantly affected the smaller protoplanets. In the early stages, Jupiter and Saturn moved closer to the Sun, dragging the wet protoplanets along and causing them to collide with the dry protoplanets. The result was a series of new planets, one of which was the primordial Earth. Therefore, Earth's water, both its oceans and fresh water, originated from the wet protoplanets of the early solar system. This theory explains the presence of water on Earth without resorting to cometary sources. Further supporting this theory is evidence from the asteroid belt, such as the dwarf planet Vesta, which originated from primordial asteroids. Water in Vesta has a deuterium content that matches Earth's water, suggesting a similar source for both. However, the conundrum remained more than 10 million years after Earth formed. A cataclysmic event led to the creation of the dual planetary system Earth and its moon. The prevailing theory suggests that a Mars-sized planet collided with Earth, ejecting material that later formed the moon. But such a violent collision would have raised temperatures on Earth's surface enough to vaporize its oceans and lakes. How the Earth's water environment recovered after such an event is still a mystery, but May's theory does not solve. Yet, Moses offers an explanation. After the collision, while Earth's surface was a sea of molten lava, it acted as an efficient water-absorbing sponge. When the temperature dropped, as lava formed volcanic rocks, trapping water within them. Over time, water from the volcanic rocks evaporated and reformed Earth's oceans and lakes. This explanation has been further supported by recent research published in the journal Physical Review Letters. Scientists working at the Sky Institute and in China have suggested that water, or at least its components hydrogen and oxygen, could have existed since Earth's formation. This implies that other planets might also contain water. About 70% of Earth's surface is covered by water, of which 97% is in the oceans, and only about 3% exists in other forms like rivers, glaciers, and groundwater. According to Professor Atnungen, co-author of the study, some theories suggest that comets brought water to Earth, but this source seems limited because the isotopic composition of water in comets is vastly different from that on Earth. Water didn't come from extraterrestrial sources. It must have originated from beneath Earth's crust or even from its core. The challenge was to explain how water could persist through 4.5 billion years of tumultuous history, including colossal impacts from outer space and the formation of the Earth's core. To address this, the scientists propose that a chemical compound, though no longer present, could have detected subsurface water through this turbulent era, using computational methods to predict crystal structures. Huggins' team discovered a suitable compound, magnesium hydroxylate, which contains over 11 and water by weight and is stable at pressures over 2 million atmospheres and extreme temperatures, conditions found in Earth's core. Magnesium hydroxylate could shield water deep within the core from the very beginning. As bombardments from space in the core's formation process pushed hydroxylate into lower pressure regions, it became unstable and decomposed, releasing magnesium oxide and magnesium silicate to form Earth's mantle. along with water. This new theory about water's origins also implies that life-sustaining planets in the universe need to have both continents and oceans, thus containing water, albeit not in large quantities. Extrapolating from Earth's conditions, a life-bearing must have about 0.2% of its mass as water. For larger planets, known as super-Earths, this amount must be greater. The stability of magnesium hydroxide could protect substantial water reserves indefinitely. This theory not only explains aqueous origins, but also on Earth being too small to generate the necessary pressure for magnesium hydroxide to remain stable, is arid and lacks water. In conclusion, the origins of Earth's water remain a topic of extensive scientific inquiry, with theories ranging from cometary impacts to intrinsic formation. As research continues, our understanding of water's provenance and its role in shaping planetary environments will undoubtedly deepen. The pursuit of this knowledge not only illuminates our past, but also guides the search for life beyond our planet. The presence of water, a key ingredient for life as we know it, could suggest that planets with semi-hydrogen to Earth may also harbor life. Understanding the origins of water on Earth helps to frame our search for exoplanets with conditions favorable for life. If water can be intrinsic to a planet's formation, and not solely reliant on external sources like comets, then the potential for finding water-rich planets increases. This realization expands the scope of habitable zones around stars, beyond regions where water can remain liquid on a planetary surface. Furthermore, the study of water's origins on Earth has implications for planetary protection and space exploration policies. If future missions discover water or its components on other planets or moons, it could indicate past or present conditions suitable for life. This makes the protection of these celestial bodies from contamination by Earth organisms even more crucial. The research also emphasizes the complexity of planetary formation, in a myriad of factors that contribute to a planet's development. From the composition of the primordial solar nebula to the gravitational dynamics of early protoplanets. Each step in Earth's formative process has played a role in creating the conditions necessary for our oceans and atmosphere. As we continue to explore our solar system and beyond, missions such as NASA's Perseverance rover on Mars or the Europa Clipper mission to Jupiter's icy moon are designed to search for signs of water and, by extension, life. By understanding how water came to be on Earth, we can better design these missions to look for similar processes on other worlds. In the end, the quest to understand water's origins on Earth is a quest to understand our own origins. It's a narrative that connects the microcosm of atomic particles to the macrocosm of planetary bodies, weaving a story of cosmic proportions that spans billions of years. It is a reminder that water, so vital to our existence, may be more than a resource. It could be a cosmic signature of life's potential throughout the universe.